Welcome to Chapter 4, Complex Numbers and Quadratic Equations. We know that x squared plus 1 equals 0 has no real solution since squares are always non-negative. To solve such equations, we extend the real number system to include complex numbers. This powerful extension, developed by W.R. Hamilton, allows us to solve all quadratic equations. A complex number has the form z equals a plus ib, where a and b are real numbers. Here, a is called the real part, written rez, and b is called the imaginary part, written imz. The symbol I is the imaginary unit, defined by the property that I squared equals -1. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So if z1 equals a plus ib and z2 equals c plus id, then z1 equals z2 precisely when a equals c and b equals d. This is a fundamental property we use constantly. Adding complex numbers is straightforward. Add real parts and imaginary parts separately. If z1 equals a plus ib and z2 equals c plus id, then z1 plus z2 equals a plus c plus I times b plus d. Addition is commutative and associative. The additive identity is 0 plus I0, and every complex number has an additive inverse. Multiplication uses the rule I squared equals -1. The product of a plus ib and c plus id equals ac minus bd plus I times AD plus BC. Multiplication is also commutative and associative, has identity 1 plus I0, and every non-zero complex number has a multiplicative inverse. The powers of I follow a beautiful pattern. I squared is -1, I cubed is I to the fourth is 1. Then the pattern repeats. I to the fifth is I to the sixth is -1, and so on. In general, I to the power 4k is 1, I to the power 4k plus 1 is I to the power 4k plus 2 is -1, and I to the power 4k plus 3 is I. We can now take square roots of negative numbers. The square root of -1 is I. More generally, the square root of -a, where a is positive, equals I times the square root of a. For example, the square root of -3 equals I times root 3. Both I and -I are square roots of -1. The modulus of a complex number z equals a plus ib is defined as the square root of a squared plus b squared. We write it as z. It represents the distance from the origin in the complex plane. For example, the modulus of 3 plus 4i is the square root of 9 plus 16, which equals 5. The conjugate of a complex number z equals a plus ib is z bar equals a minus ib. We simply change the sign of the imaginary part. Important properties. Z times z bar equals z squared. Z plus z bar equals 2a, which is twice the real part. Z minus z bar equals 2ib, which is 2I times the imaginary part. Division of complex numbers uses the conjugate. To divide z1 by z2, we multiply both numerator and denominator by z2 bar. This gives us z1 times z2 bar divided by z2 squared. The denominator becomes a real number, making the result easy to express in standard form a plus ib. The Argand plane provides a geometric representation of complex numbers. The x-axis represents the real part, and the y-axis represents the imaginary part. A complex number a plus ib corresponds to the point AB in this plane. This visual representation helps us understand operations like addition and multiplication geometrically. Complex numbers can also be written in polar form. Z equals r times cos theta plus I sine theta, where r is the modulus and theta is the argument, the angle from the positive x-axis. This is also called the modulus argument form. Euler's formula connects this to exponentials. E to the power I theta equals cos theta plus I sin theta. Now we can solve quadratic equations with negative discriminants. For x squared plus bx plus c equals 0, the discriminant d equals b squared minus 4ac. When d is negative, the solutions are complex. We use the quadratic formula x equals -b plus or minus the square root of d, all divided by 2a. The square root of -d becomes I times root d. Let's solve x squared plus x plus 1 equals 0. The discriminant is 1 minus 4, which equals -3. Since d is negative, we have complex roots. Using the quadratic formula, x equals -1 plus or minus I times root 3, all divided by 2. These are two complex conjugate roots. Important properties of conjugates and modulus. The modulus of a product equals the product of moduli. The modulus of a quotient equals the quotient of moduli. The conjugate of a sum equals the sum of conjugates. The conjugate of a product equals the product of conjugates. These properties simplify many calculations. Standard algebraic identities work for complex numbers too. The square of a sum, z1 plus z2, squared equals z1 squared plus z2 squared plus 2z1 z2. The square of a difference, z1 minus z2, squared equals z1 squared minus 2z1 z2 plus z2 squared. And the difference of squares, z1 squared minus z2 squared equals z1 plus z2 times z1 minus z2. The multiplicative inverse of z equals a plus ib is 1 over z equals z bar over z squared. This equals a minus ib divided by a squared plus b squared. In standard form, a over a squared plus b squared minus I times b over a squared plus b squared. We find this by multiplying numerator and denominator by the conjugate. Complex numbers have countless applications. In electrical engineering, they analyze AC circuits using impedance. In quantum mechanics, wave functions are complex valued. Signal processing uses complex numbers for Fourier transforms. Control systems use them for stability analysis. They're essential tools in modern science and engineering. Watch out for common mistakes. Never write square root of -1 times square root of -1 equals square root of 1 equals 1. This is wrong. Remember that square root of -a equals I times root a, not negative root a. And I squared equals -1, not 1. The conjugate only changes the sign of the imaginary part. Here are the key formulas to remember. I squared equals -1. A complex number z equals a plus ib has modulus z equal to the square root of a squared plus b squared. Its conjugate z bar equals a minus ib. The product z times z bar equals z squared. And the quadratic formula works for complex roots when the discriminant is negative. When solving problems with complex numbers, use conjugates to simplify expressions. Use modulus properties for multiplication and division. Convert to polar form when dealing with powers. Always check the discriminant to determine if a quadratic has real or complex roots. To find powers of I, divide the exponent by 4 and use the remainder. For I to the 17th power, 17 equals 4 times 4 plus 1, so the remainder is 1, giving I. For I to the 100th power, 100 equals 4 times 25 plus 0, so the remainder is 0, giving 1. For negative powers, I to the minus n equals 1 over I to the n. Geometrically, addition of complex numbers is vector addition in the Argand plane. The modulus represents distance from the origin. The conjugate is the reflection in the real axis. Multiplication by a complex number involves both scaling and rotation. The modulus scales by the product of moduli, and the angle adds. Real numbers are complex numbers with zero imaginary part. They're of the form a plus 0i. Purely imaginary numbers have zero real part. They're of the form 0 plus bi. Real numbers are a subset of complex numbers. Complex numbers complete our number system, allowing us to solve any polynomial equation. In this chapter, we learned that complex numbers extend the real numbers to solve equations like x squared plus 1 equals 0. A complex number has the form a plus ib with real part a and imaginary part b. We studied addition, subtraction, multiplication, and division of complex numbers. The modulus and conjugate are key concepts. Quadratic equations can have complex roots when the discriminant is negative. Thank you for joining Chapter 4 on complex numbers and quadratic equations.